Next, we want to look at complex numbers written in trigonometric form. And you can see over here on the board, I've written that the complex number x plus yi, its graph will be the vector that goes from the origin out to the point xy. Well, if that's true, then we can let r be the distance from the origin out to that point. That's the absolute value or modulus of that complex number. And then theta is the angle that the vector makes with the positive x-axis. So using trigonometry, then I can derive the fact that x plus y times I is the same as r times cosine theta plus I sine theta. This is in what we call standard form, and this now is in what we call trigonometric form. So if you want to see the actual derivation of this, you'll have to read the book. But it's all based on this diagram right here, which really goes back to our simple definition for the trigonometric functions from either Chapter 1 or Chapter 2. Let's try one of these problems. Here I've written, write -1 plus I in trigonometric form. So I have x plus 1 times I. So it's -1 plus 1 times I. I have the real part and the imaginary part in standard form. I want to write it in trigonometric form, so what I need is r, and I also need theta. So let's graph this complex number, -1 plus I, and see if we can make it easy on ourselves. I'll make this -1. This will be 1. So I'll go out to this point right here. This vector that goes from the origin out to the point -1, 1 is the graph of the complex number -1 plus 1 times I. Well, I know from simple trigonometry and the distance formula that the distance from the origin out to the point -1, 1 is going to be square root 2. I also know that this angle right here must be 135 degrees because this vector goes right in between the two axes there. So it splits that quadrant, so that's 135 degrees. Therefore, this complex number, -1 plus I, in standard form, must be equal to square root 2 cosine of 135 plus I times the sine of 135 degrees. So trigonometric form for this complex number, square root 2 times cosine 135 plus I sine 135. Let's look at another problem. This time we want to take the complex number 2 times the quantity cosine 30 plus I sine 30 that's written in trigonometric form and write it in standard form. Let's just sketch the graph of this real quick as long as we've got it here. I'll draw a vector at 30 degrees with a length of 2. So there's the graph of that complex number 2 times cosine 30 plus I sine 30. To write this in standard form, I simply look up these values. I'll use exact values right here. Cosine of 30 is square root 3 over 2 plus I times the sine of 30 is 1/2. Then I'll multiply 2 times this fraction, and I'll have square root 3. 2 times this fraction, and I'll have 2 times I times 1/2, which will just be I. So in standard form, this complex number 2 cosine 30 plus I sine 30 turns out to be just square root 3 plus I. And here you can see the graph right here. This means that this ordered pair xy that's at the tip of this vector must be the ordered pair square root 3 and 1. Let's look at another problem. Cosine 210 plus I sine 210. Okay, I want to write this in standard form also instead of trigonometric form. Let's draw its graph. 210 degrees is 30 degrees past 180. So I'll draw it like this. And this has a modulus or absolute value of 1. So I'll make it half as long as that one. So it has a length of 1. And this angle right here is 210 degrees. So if I want to write this now in standard form, I'll simply look these up. Cosine of 210, well, the reference angle is 30 degrees. 210, you can see, terminates in quadrant 3. So I have negative square root 3 over 2 plus I times sine 210. The reference angle is 30. Sine of 30 is 1/2. And in quadrant 3, it's negative, so negative 1/2. So I end up with negative square root 3 over 2 minus 1/2 I for that complex number written in standard form. So going from trigonometric form to standard form is really very direct. You just simply look up the values of these trig functions and then simplify until you get something that looks like it's written in standard form. Let's look at another problem here. Let's write 8i in trigonometric form. We'll go back the other way. Well, 8i is the complex number 0 plus 8i. So the graph of this complex number 8i is going to be the vector that goes from the origin out to the point 0, 8. So I'll just make this 0, 8. There's the graph of that complex number. It's easy to see by looking at this that that length of the vector is 8 and that this angle right here is 90 degrees. So if I want to write this complex number that's written in standard form in trigonometric form, it will be 8 cosine 90 plus I times the sine of 90. So it's just that simple to go from the graph of this complex number written in standard form to the same complex number written in trigonometric form. Now let's work another problem in which we have to do a little bit more work to find that angle. Let's write 3 plus 4i in trigonometric form. Well, let's begin by graphing this complex number. It's the vector that goes from the origin out to the point x equal 3 and y equal 4. So that's going to be this point right here. So that vector looks like that. Now I know that with this right triangle right here, this is 3, this is 4, so this must be 5 by the Pythagorean theorem. So I have r is equal to 5. The only other thing I need to find is theta. So theta right here is going to be the inverse tangent of 4/3. So it's the angle whose tangent is 4/3. Now that's its exact value. I'll look it up on the calculator just to give me an approximate value for this. If I put in 4/3 in the calculator, press the inverse tangent button, I get 53.1 degrees. Let's just round to the nearest degree. So I'll take this value of r, this value of theta, and I'll write 3 plus 4i in trigonometric form as 5 cosine 53.1 degrees plus I times the sine of 53.1 degrees. So I should probably write approximately right here because this angle is not it exactly. The exact value for this angle would be inverse tangent 4/3. But just so that I have something to write, I'll go to my calculator, work this problem, get 53.1. Now I have my complex number in trigonometric form with an r and a theta right here. So this is approximately what it is. This would be exactly what it was if I used that. So there's a look at how we go back and forth between standard form and trigonometric form for complex numbers.